So in 2012, a spacecraft that had been traveling for 35 years crossed what was believed to be the edge of the solar system. The moment was declared historic. Press conferences were held at NASA headquarters. Papers were published in the most prestigious journals in physics. Headlines on every major news outlet in the world said humanity had officially entered interstellar space for the first time. The boundary had been crossed. The solar system was behind us. The galaxy was ahead. And then the data started coming back from the other side. And the data was wrong. Not wrong as in the instruments had malfunctioned or the telemetry was corrupted or a software error had produced bad numbers. Wrong as in what the spacecraft found on the other side of the boundary did not match what a single model on Earth had predicted it would find. The temperature was wrong. The magnetic field was wrong. The structure of the boundary itself was wrong. And now, more than 12 years later, a growing number of researchers studying that data are asking a question that would have been unthinkable at the 2012 press conference. What if the spacecraft never actually crossed the edge? What if the edge is not a line at all? What if it is a region, thick and violent and magnetically chaotic and shifting from year to year, and the spacecraft has been traveling through it for 12 years at 17 kilometers per second and still has not come out the other side? I am Graham Prescott, and if stories like this are what you come here for, subscribe right now because we are just getting started. To understand what was expected, you need to understand what every model of the solar system's boundary predicted the crossing would look like. The sun produces a constant stream of charged particles called the solar wind. That wind blows outward in every direction, inflating a magnetic bubble called the heliosphere that extends far past the orbit of Pluto, wrapping the entire solar system in a protective cocoon. Beyond that bubble is the interstellar medium, the thin gas and dust and magnetic field that fills the space between stars. Where the outward pressure of the solar wind balances the inward pressure of the interstellar medium, a boundary forms. That boundary is called the heliopause, and it was understood for decades to be a clean transition. A line, solar system on one side, interstellar space on the other. The models describe what crossing it should feel like in precise, testable terms. The magnetic field should rotate sharply, because the sun's magnetic field and the galaxy's interstellar magnetic field point in different directions. The particle density should change abruptly, because the solar wind and the interstellar medium have very different densities. The temperature should drop, because you are leaving the warm solar wind and entering the cold interstellar medium. And the transition should be brief. A spacecraft traveling at 17 kilometers per second should pass through the boundary in a matter of hours, maybe days, like stepping from a heated house into cold night air. One step, inside to outside, warm to cold, solar to interstellar. Done. That was the expectation. A door between two rooms. What the spacecraft found was not a door. It was a burning hallway between two rooms, and the hallway is still going. On August 25, 2012, NASA's Voyager 1 reached the heliopause. It had been traveling since September 5, 1977, launched from Cape Canaveral on a Titan IIIe rocket with a 5-year mission to photograph Jupiter and Saturn. That was 35 years earlier. The spacecraft had long since completed its original mission, survived the punishing radiation belts of Jupiter that degraded some of its instruments, captured the iconic pale blue dot photograph of Earth from nearly 4 billion miles away, in which our entire planet is a single pixel suspended in a scattered beam of sunlight, and coasted silently through the outer solar system decade after decade on a trajectory that would eventually carry it beyond everything the sun can touch. Its plutonium power source was slowly decaying, losing roughly 4 watts per year, and its instruments were being shut down one by one to conserve the remaining power. But the magnetometer was still running, the plasma wave system was still running, the cosmic ray detector was still running. And when Voyager reached the heliopause, those instruments confirmed the crossing in particle terms that were unambiguous. The density of solar wind particles dropped to near zero. The density of galactic cosmic rays, high-energy particles originating from outside the solar system, increased sharply. Energetic particle counts changed in exactly the way the models predicted they would change, at the transition from heliospheric to interstellar plasma. By every particle measurement available, Voyager 1 had left the heliosphere. It was in interstellar space. The crossing was real. NASA held a press conference. The moment was declared the most significant milestone in the history of space exploration since the moon landing. Papers were published in Science. The crossing date, August 25, 2012, was entered into the permanent record of human achievement. But the temperature was not what the models predicted. Instead of a cold, quiet transition into the frigid interstellar medium, Voyager 1 encountered temperatures at the boundary approaching 30,000 degrees Celsius. 30,000 degrees. For context that makes this number feel real, the surface of the Sun is approximately 5,500 degrees Celsius. The filament inside a standard incandescent light bulb operates at roughly 2,500 degrees. The melting point of tungsten, the most heat-resistant common metal, is 3,422 degrees. 30,000 degrees exceeds all of these by an order of magnitude. The heliopause, the outermost edge of the solar system, the boundary between our star's domain and the galaxy's interstellar medium, was hotter than the surface of the star that created it. This was not in any model, not in any simulation published by any heliophysics research group, not in any prediction from any institution in any country. Every model predicted that the transition would be cool, gradual, and quiet, a slow fade from solar-dominated plasma to interstellar-dominated plasma. Instead, a wall of fire. The cause, determined through years of subsequent analysis, was magnetic reconnection. At the heliopause, the Sun's magnetic field lines, which have been carried outward by the solar wind and stretched across billions of kilometers, collide with the interstellar magnetic field lines, which are being pushed inward by the pressure of the local interstellar medium. When magnetic field lines from two different sources meet at angles, something violent happens. The lines break. They snap apart and reconfigure into new orientations, releasing the magnetic energy that was stored in their tension as kinetic and thermal energy. This process, magnetic reconnection, is the same mechanism that powers solar flares on the surface of the Sun. At the heliopause, it happens continuously, everywhere along the boundary, as the two magnetic systems press against each other and their field lines tangle, break, reform, tangle again, break again. The mechanical motion of the compressed plasma converts to heat, and the result is a superheated sheath of plasma wrapping around the entire edge of the solar system like a membrane of fire. The spacecraft survived because the plasma at the heliopause is extraordinarily thin. 30,000 degrees refers to the kinetic energy of the individual particles, the speed at which individual ions and electrons are vibrating, not to the total thermal energy being transferred to the spacecraft. Each particle is ferociously energetic, but there are so few of them per cubic centimeter, far fewer than the thinnest vacuum achievable in any laboratory on Earth, that the actual heat load on the spacecraft is negligible. Like sparks from a campfire landing on your skin on a cold night, each individual spark is genuinely 1,000 degrees or more, but there are so few of them hitting any given square centimeter of your skin at any given moment that you feel a brief pinprick of warmth, not a burn. The heliopause is 1,000,000,000,000 sparks at 30,000 degrees, spread across billions of cubic kilometers of nearly empty space, hot by particle energy, cold by thermal transfer. The edge of the solar system is not cold and silent. It is hot and violent and wrapped in a magnetic fire that no model predicted, and nobody knew it was there until a spacecraft built in the 1970s flew through it and measured it for the first time. But the temperature was only the first surprise. Because when Voyager measured the magnetic field on the other side of the boundary, what it found was something that should have been impossible. Every model of the heliopause crossing predicted that the magnetic field direction would change dramatically when the spacecraft passed from the heliosphere into interstellar space. This was considered one of the most certain predictions in all of heliophysics. The Sun's magnetic field and the galaxy's interstellar magnetic field originate from completely different sources, are shaped by completely different processes, are maintained by completely different dynamo mechanisms, and point in completely different directions. The Sun's field is generated by currents deep inside the solar interior and carried outward by the solar wind, twisted into a spiral pattern by the Sun's rotation. The interstellar magnetic field is generated by the large-scale dynamo of the Milky Way galaxy itself, and threaded through the local interstellar medium at an orientation that has been estimated by multiple independent spacecraft missions and astronomical observations. The two fields are not aligned. Crossing from one domain to the other should produce a sharp, unmistakable rotation in the magnetic field direction measured by any magnetometer on any spacecraft passing through, the same way a compass needle swings when you carry it from one magnetic environment into a fundamentally different one. When Voyager 1 crossed the heliopause in August 2012, the magnetic field barely changed at all. Almost no rotation in direction. Almost no change in magnitude. The data from the magnetometer showed a boundary crossing confirmed by every particle instrument on board. Cosmic ray counts, solar wind density, energetic particle flux, all consistent with having left the heliosphere. But the magnetic field on the other side looked almost identical to the magnetic field on the side Voyager had just left. This was so confounding, so directly contradictory to the predictions, that it generated years of heated, at times bitter, debate within the heliophysics community. Some researchers openly questioned whether Voyager had actually crossed the heliopause at all. If the magnetic field did not change, they argued, perhaps the spacecraft was still inside the heliosphere, and the particle changes were caused by some local disturbance, a transient event, a merged interaction region, a fluctuation that mimicked the particle signature of a boundary crossing without actually being one. Others argued the crossing was real, but that the magnetic environment outside the heliosphere was not what decades of remote sensing had led everyone to believe. Physics Today published an article with the headline, "The Confounding Magnetic Readings of Voyager 1." The measured direction of the local interstellar magnetic field was more than 40 degrees off from what the Interstellar Boundary Explorer satellite, the Ulysses Solar Orbiter, and ground-based astronomical observations using starlight polarization had independently determined it should be. 40 degrees is not a calibration issue. It is not within the margin of error. It is a fundamental disagreement about the direction of the magnetic field in the region of space that Voyager was supposed to be traveling through. The edge is not a line, because at a line, the field changes. At a line, you know when you have crossed. The field did not change. And for years, nobody could explain why. Imagine walking through a door between two rooms and discovering that the room on the other side has the same wallpaper, the same furniture, the same lighting, the same temperature. You were told the rooms would be completely different. They are not. And now you are not sure whether you actually walked through a door at all, or whether the door was never there. The answer, when it finally came, did not make the situation simpler. It made it stranger. In January 2024, Drew Turner and colleagues published a paper in the Astrophysical Journal that re-examined both Voyager 1 and Voyager 2 data from the heliopause region, with the benefit of more than a decade of accumulated measurements from both spacecraft operating on opposite sides of the boundary zone. Their conclusion did not just update the existing models, it replaced them. The heliopause is not a thin boundary line. It is not a surface. It is not a membrane you pass through. It is a thick boundary layer. A region of space, potentially tens of astronomical units across, where magnetic reconnection is happening continuously on scales large and small. Solar magnetic field lines and interstellar magnetic field lines are colliding, breaking apart, reforming into new configurations, breaking again, colliding again, in an endless cycle of magnetic violence that produces the wall of fire temperatures, the confounding magnetic readings, and the anomalous cosmic ray behavior that both Voyager spacecraft have documented. Turner's paper directly addresses the magnetic field mystery. This paper offers a mechanism to explain the mystery of why the direction of the magnetic field did not change at the Voyager crossings of the purported heliopause. The key word is purported. The paper does not take for granted that the 2012 event was the true heliopause crossing. It proposes that what Voyager entered in 2012 was the beginning of the boundary layer, not its end. The interstellar magnetic field is draped around the heliosphere, stretched and deflected by the three-dimensional shape of the solar bubble, like an elastic cord wrapped around a beach ball, in the widely cited analogy of Nathan Schwadron at the University of New Hampshire. Inside the draping zone, the field direction is rotated away from its true orientation by the geometry of the bubble itself. You cannot measure the undistorted interstellar field from inside the draping zone any more than you can measure the true tension of a rubber band while it is stretched around an obstacle. You have to travel through the entire draping region, all the way through the thick boundary layer, to reach the field in its natural, undistorted, pristine state. And Voyager has not done that yet. The paper predicts that Voyager 1 will not reach the pristine interstellar medium until approximately a decade after the 2012 crossing, meaning sometime around 2025, at the earliest and more likely the early to mid-2030s, depending on the actual thickness of the layer and any variability it encounters along the way. 12 years after the press conference, 12 years after the headlines, 12 years after humanity was told it had entered interstellar space, and the spacecraft may still be inside the boundary, not inside the heliosphere, not fully in interstellar space, in between, in the hallway. Some researchers go even further. Leonard Fisk and George Gluckler have proposed in multiple papers that Voyager 1 did not cross the true heliopause in 2012 at all. They point to a feature in the magnetometer data called PF2, a distinct magnetic enhancement that appeared in the data years after the 2012 event, and argue that PF2, not the 2012 crossing, represents the actual outer boundary of the heliosphere. If they are correct, then the event that was celebrated around the world as the greatest boundary crossing in the history of space exploration was not a passage through the edge. It was an entrance into the boundary layer. The crossing everyone celebrated was the beginning of the transition, not the end of it. The edge is not a line, it is a region. And the region is thick enough that a spacecraft traveling at 17 kilometers per second has been inside it for 12 years and may not have come out yet. We thought the edge was a wall. Walk through it, you are outside. What Voyager found is that the edge is more like a coastline, not a clean line between land and sea, a muddy, shifting tidal zone where both worlds mix and neither one fully owns the ground. If the boundary is thick and Voyager has been inside it for 12 years, then what does the boundary look like from year to year? The answer is that it moves. If the boundary is thick and Voyager has been inside it for 12 years, then what does the boundary look like from year to year? Is it stable? Is it the same structure every time a spacecraft encounters it? The answer is that it is not. The boundary moves, and it moves more dramatically than anyone expected. Voyager 1 crossed the heliopause in August 2012 at a distance of approximately 122 astronomical units from the Sun. That is 122 times the distance between the Earth and the Sun, roughly 11.5 billion miles. Voyager 2, traveling on a different trajectory through a different region of the heliosphere, crossed the heliopause in November 2018 at a different distance under different conditions. The magnetic field readings were different. The particle transition profiles were different. The precise characteristics of the boundary layer were different. In October 2022, Eric Zernstein and colleagues at Princeton University published a paper in Nature Astronomy examining these discrepancies in detail, comparing the two crossings side by side, and their conclusion was stark. The heliopause changed dramatically in a very short period of time. The researchers described their own findings as intriguing and potentially controversial, language that in the measured vocabulary of academic astrophysics signals something that the authors themselves find difficult to fully explain. If the edge were a fixed line, a permanent boundary at a specific, stable distance from the Sun, both spacecraft should have crossed at similar distances under broadly similar conditions, even accounting for the fact that they were traveling through different sectors of the heliosphere. The differences should have been modest, predictable, within the range of variation that existing models could accommodate. They were not. The heliosphere breathes with the 11-year solar activity cycle, expanding outward during solar maximum when the solar wind blows hardest, and contracting inward during solar minimum when the wind weakens. That breathing is well understood and well modeled. But the differences between the Voyager 1 and Voyager 2 crossings were larger than the solar cycle breathing alone can explain. The boundary did not just pulse gently in and out, it restructured, it reorganized. Something about the interstellar medium's pressure, or the heliosphere's internal dynamics, or both, changed between 2012 and 2018 in ways that produced a boundary that looked fundamentally different to the second spacecraft than it had to the first. The coastline moved kilometers between one crossing and the next. The edge is not just thick, it is alive. It shifts, it transforms. It is not the same boundary from decade to decade. And the two spacecraft that crossed it 6 years apart found two different versions of the same place. And then, once Voyager was through the fire and inside the boundary layer, and recording measurements from a region no instrument in human history had ever sampled directly, it heard something that no model predicted would exist. Something that had been happening apparently continuously, without interruption, for as long as Voyager's instruments have been sensitive enough to detect it. In 2021, Stella Koch-Ucker, a doctoral student in astronomy at Cornell University, published a paper in Nature Astronomy announcing the discovery of a faint, continuous, narrowband plasma wave emission hiding in the Voyager 1 plasma wave system data, a hum, not triggered by solar events. Not intermittent, not a one-time detection that could be dismissed as a fluke, persistent, present in the data from at least 2017 onward, and possibly longer, never stopping, never changing frequency, never pausing. We're detecting the faint, persistent hum of interstellar gas, Ucker said when the discovery was published. It's very faint and monotone, because it is in a narrow frequency bandwidth. The signal had been hiding just above the noise threshold of the instrument, so close to the background that it had been overlooked in the initial analyses of the post-crossing data. Her senior colleague James Cordids at Cornell described the interstellar medium in terms that sounded more like weather than like the vacuum of space. The interstellar medium is like a quiet or gentle rain, he said. Between the occasional thunderclaps of solar shockwaves propagating outward from the Sun and ringing the plasma like a bell, there was this continuous drizzle of activity that nobody had detected because nobody had an instrument out there to detect it, and nobody expected it to be there even if they did. The interstellar medium was supposed to be silent between shock events, dead, featureless, empty of activity at any frequency that Voyager's instruments could detect. Instead, a sound, a low, continuous, narrowband vibration in the plasma that traces turbulence at astronomical unit scale, revealing structure and activity in the space between stars that the models had not accounted for. Standing in what you were told is a perfectly silent room. You hold your breath, you listen, and there it is, a low, steady hum, right at the edge of what your hearing can detect, and it never stops. It has been going on for years, maybe longer, maybe always, and nobody knew because nobody had ever stood in this room before. The edge is not a line. And what lies beyond the edge is not silence, it is a voice. The interstellar medium has been speaking the entire time. We just never had anyone out there to hear it. The boundary is thick, hot, magnetically confusing, temporally variable, and beyond it there is a sound that should not exist according to every model that was built to describe it. And for the first time, multiple missions are converging on the boundary simultaneously. IMAP, NASA's Interstellar Mapping and Acceleration Probe, launched in September 2025, is now stationed at Lagrange Point 1.5 million kilometers from Earth, mapping the heliosphere from the inside by detecting energetic neutral atoms that travel in straight lines from the boundary back to the detector. Its science phase began in February 2026. Over 2 years, it will build the first comprehensive three-dimensional map of the heliosphere ever created, showing where the boundary is thicker, where it is thinner, where the interstellar medium is pushing harder, and where the draping of the magnetic field is most extreme. New Horizons, the spacecraft that gave us our first close-up images of Pluto in 2015, is heading toward the outer heliosphere and may cross the termination shock, the inner boundary where the solar wind drops from supersonic to subsonic speed, as early as 2029. If it does, it will enter the heliosheath, the turbulent buffer zone between the termination shock and the heliopause, carrying instruments far more sophisticated than anything the Voyagers had. Instruments designed with the benefit of knowing what the Voyagers found and calibrated to test the thick boundary layer model directly. And Voyager 1 itself is still out there, still traveling, still measuring. Its magnetometer and plasma wave system are still operating, still sending data home at 22 watts of transmission power across a signal path that takes more than 22 hours one way. The magnetic compass needle, the field direction measured by the magnetometer, has been slowly, gradually rotating toward what scientists estimate is true magnetic north, the direction of the pristine interstellar magnetic field, undistorted by the heliosphere's shape. When the compass reaches true north, if it reaches true north before the power runs out, Voyager will have exited the boundary layer and entered the pristine interstellar medium for the first time in the true sense of the word. It has not arrived yet. The needle is still rotating, but it is getting closer. Nathan Schwadron at the University of New Hampshire put it directly. When Voyager 1 crosses that next boundary, we will be poised to probe many long-standing mysteries about the interstellar medium and our galaxy's magnetic field. There is a next boundary. The thick layer has another side. Voyager is heading toward it, at 17 kilometers per second, on a power budget that loses 4 watts every year. The race between the compass reaching true north and the plutonium running out is the quietest, slowest, most consequential race in the history of space exploration. We sent a machine to find the edge of the solar system. It found the edge. And then it discovered the edge is wider than anyone imagined, and it has not finished crossing. Every map has edges, lines where one color ends and another begins. Our territory here, the unknown there. Clean borders, sharp boundaries, the kind of edges that fit neatly into a legend at the bottom of the page. We assumed the solar system's edge would be like that, a line on the cosmic map. Inside the line, the sun's domain, the planets, the asteroids, the comets, the Kuiper belt, everything familiar and governed by our star. Outside the line, the galaxy, interstellar space, the unknown. One step across, and you have left home. Voyager went to that line and found something different. The edge is a place, not a line, not a surface, not a membrane. A thick, hot, magnetically violent, acoustically alive, temporally shifting place that extends for years of travel at 17 kilometers per second. A place where the sun's magnetic field and the galaxy's magnetic field collide and break and reform continuously, releasing enough energy to heat the plasma to 30,000 degrees Celsius, hotter than the surface of the star that inflated the bubble in the first place. A place where the magnetic compass reads 40 degrees off from true north, Because the field is draped and twisted by the geometry of the bubble it is pressed against, stretched like an elastic cord around a beach ball, distorted in ways that make it impossible to determine the undistorted interstellar field direction until you have traveled all the way through the draping zone, a place that moves between decades, restructuring itself on timescales shorter than the interval between the two spacecraft crossings, changing its shape and its properties and its distance from the sun in ways that existing models cannot fully explain. A place where, beyond the fire and the magnetic confusion and the shifting boundaries, a continuous hum has been playing since at least 2017, the sound of interstellar turbulence at a scale measured in astronomical units, heard for the first time by a machine that was never designed to hear it, in a location where every model said there would be nothing to hear. We thought we knew where the solar system ends. Voyager went there and found that the ending is not a moment. It is a journey. A 12-year-long journey through fire and silence, and magnetic confusion, and a hum that should not exist. And the journey is not over. The compass has not reached true north. The pristine interstellar medium has not been touched. The hallway is still going. The plutonium is still decaying. The power is still dropping. 4 watts less every year. And the quietest, slowest race in the history of human exploration continues. The compass needle rotating toward true north. The wattage ticking down toward zero. And somewhere ahead, beyond the draping and the fire and the turbulence, the pristine interstellar medium is waiting. Undistorted, unmixed, the galaxy in its natural state. Nobody has ever measured it directly. Voyager might be the first. If it gets there before the power runs out. If the compass reaches true north before the plutonium cools past the point of no return. The edge is not a line. It never was. If this kind of story is what you come here for, subscribe right now and turn on notifications, because next time we are covering what IMAP's first data is revealing about the true shape of the heliosphere from the inside. And the early maps do not match the models. Drop a comment with what surprised you most. The 30,000 degrees at the boundary, the magnetic field that refused to change direction, the possibility that after 12 years, Voyager still has not reached pristine interstellar space, or the hum that has been playing in a place where every model predicted silence. And share this with someone who thinks we have the solar system figured out, because the edge just got a lot more complicated than anyone imagined.